Hello, everyone. My name is Jimmy, and today we're going to be talking through a topic that I believe is fundamental to applying machine learning in the real world, and it's called completing the machine learning loop. So before we get started, let me tell you a little bit about myself. So my name is Jimmy Whitaker. I'm a machine learning developer and developer advocate at Pachyderm, where we're trying to solve some of the hardest data logistics problems in machine learning. So I joined Pachyderm after leading and working in applied research teams that were building NLP and speech recognition models for financial institutions. And what I ran into, or while applying these models, we were constantly running into issues that centered on data management, iterative model improvements, and the scalability of our tooling and process. So many of the things that we're going to talk about today are things that I've at least dealt with firsthand, and hopefully sharing this experience and talking through some of the ways I think about it's going to help you as well. So let's take a look at the agenda. So in today's talk, we're going to frame many of the challenges in machine learning development and then talk about how we should approach them. So we're first going to start with a brief overview of machine learning and talk about the moving pieces that affect it, and have a specific focus on changing data, because that seems to be one of the things that's focused on a lot less these days. And then next, we're going to talk about some of the developments in DevOps and how these best practices actually can apply to machine learning and how that affects things. And then finally, we're going to turn our attention to a practical approach to MLOps or machine learning operations. And we're going to talk a little bit about where the world is today, what we're actually doing here at Pachyderm, and then what's going on beyond Pachyderm that's going to be ushering in the next generation of machine learning development. So we're first going to start with the question of what is machine learning. Now, everyone probably has some familiarity with machine learning if you're listening to this talk. But if we start with a very basic concepts, machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. And so in this slide, we show a comparison of traditional programming and machine learning. And the benefit of traditional programming is that we have explicitly programmed logic for anything that we want to do. Now, if we look at machine learning, we actually swap having to account for every possible situation by generalizing from examples of many situations. So, for example, if we're trying to detect the difference between a cat image or a dog image, we could do this by trying to describe every possible angle and feature of a cat or a dog in the traditional programming sense. Or we can provide a machine learning algorithm with many labeled photos of cats and dogs and train a model to predict that for us. But as soon as we move into the real world, things become a lot more complicated because we aren't just restricted to our code changes anymore. So if we take this idea of this example of a cat-dog classifier and apply it to an image like this, what happens? We're kind of in a bit of a situation because there's both a cat and a dog in this image. And so to handle an image like this, we now need to start thinking about moving to object detection from image classification. But even when we get there, we have some issues of how do we actually label the contents of this image. So, for example, the seemingly simple task to draw bounding boxes around the animals in the photo is ambiguous and can have multiple interpretations and consequences. For example, the one on the left is a single bounding box around the animals. The one in the center is a bounding box around each of the animals, but one is nested inside the other. And then the last one, there's no nested bounding boxes. However, they are the one for the dog is not capturing the entirety of that dog. And so the interesting thing here is the seemingly simple task is ambiguous, and even experts would disagree on which one is actually correct. And so the takeaway is that it really depends on the type of model that we want and even what kind of data we're going to end up seeing in production. So if our data is wrong, then our model is going to learn the wrong insights about the world. And it also takes time to apply our human expertise and understanding, because the real world is uncurated and it's full of ever increasing edge cases. I commonly refer to these issues as in these scenarios as data bugs. So they're similar to our coding bugs, but because we're in the land of machine learning, data is really our new source code. And so these data bugs can have all kinds of impacts. So some of these have huge reputational damage or even significant safety concerns. For example, there was one account of placing stickers on the road could convince Tesla's autopilot into switching lanes. And then there are many examples or studies on GPT-3 that show the the bias inside of the data set. And so that actually causes the model to exhibit racial and gender bias. And so as with coding bugs, fixing these is an iterative process. In the speech recognition world, we were struggling to define or decide rather whether to incorporate ums and uhs into our transcripts. This decision, it conveyed the real world scenario where we're hearing ums and uhs, and they could exhibit certain things such as hesitation and other types of things. But at the same time, they would hinder the readability of the transcripts, and they would even have impacts on the downstream NLP models. So this is a scenario where we were having to potentially change the labeling of the real world because of the implications that it would have downstream. And this is becoming more and more popular, where we're talking about, or this idea of centering our development on data has really grown in popularity recently with the likes of Andrew Ng and others, realizing that the power of the models, the machine learning models that we build actually comes from our data. And this makes a lot of sense. Every label that we create captures our understanding of the label or of the world at that time of labeling. And as we grow in the number of data points that we've seen, we may understand that data differently for what we actually want to get out of it. So when I talk about the machine learning loop in the context of the talk today, I define the machine learning loop as an iteration on the machine learning development system to incorporate learnings or feedback. And this could be via code or data, or even changing the approach of the technique when we iterate on this machine learning development system in one of these ways. And so this probably seems obvious, but the problem is many companies with data science teams have structured the data science process as a one-time thing. So a model development phase happens, and then we have a series of offline sequential steps that require multiple manual handoffs between teams or between individuals. And then we have this manual process to push things out to a production phase, whereby the model is deployed in whatever software application and then starts to see real world data. But the problem is, once you have a model in production, you quickly realize that your model requires iteration. So this is because production data is always different from training data. For instance, in speech recognition, there would always be a new accent or a different type of noisy environment we hadn't encountered before, or even new words that we needed to incorporate into the model's vocabulary. But when we talk about completing the machine learning loop, so what I mean by completing the machine learning loop by extension is to gracefully and consistently and reliably iterate as we improve our machine learning based systems. So this doesn't just mean we need the ability to iterate. That's almost a gimme. But when we talk about completing the machine learning loop, this means how do we do this effectively so that we can grow our organizations, so that we can enable change in our models without getting into a non-reproducible state and many other things. And so this idea of reliable iteration during development is crucial. And the good news is we're not starting from scratch here, because this is also sort of how we talk about software development, and in particular with DevOps. So we've all seen diagrams like this talking about DevOps that show the process and the iteration and all the steps that our code must go through in order to produce reliable, deployable software. So for instance, we may start with some type of a plan with what we're going to create. We then go through the process of creating it, packaging it, releasing it. And then once it's released, we're going to monitor it. And then this gives us ideas or more knowledge around how people are using the software that we wrote. And then we need to go back and incorporate new features and then continue the iteration cycle. So the key developments, if we summarize them for this shift to DevOps, is version control. So this is managing the code and version, so we can always roll back to a previous version. If something goes wrong, we have some way to reliably iterate. CI/CD, so continuous integration, continuous deployment. This has been very useful for us to be able to test our software and know that, when we made a change, this actually had adverse effects, and we need to be able to roll back or figure out what was the difference that caused the things that used to work to break. And then this iteration, this version control and CI/CD has greatly enabled more agile software development. So this is shorter release cycles, the ability to incorporate feedback quicker, and then even collaborate more inside of the team and even outside of the team. And then finally, we have continuous monitoring and infrastructure as code. So this is our means of getting feedback on the system and even getting some visibility into what's going on inside of our application. DevOps has been and still is a huge win in the software development world. And the practices and tools in particularly have really enabled DevOps, like for instance, the CI/CD systems that have come out and are continuing to come out and improve, have worked amazingly for code. We see that testing is kind of a crucial component for software development. And this all works great for code. When we move to machine learning, we have a bit of a problem because we have two moving pieces in this scenario. Because machine learning is directly dependent on both the code that we write and the data. So rather than a single development lifecycle, we now have two that are operating at the same time, and they also have dependencies on each other. The first is the code that we've talked about just now. But in the machine learning realm, we also have code that's that's written to train, test, and even deploy our software. And so that we need to manage, and we can probably manage that in the same way that we do with DevOps. But the second is the data that our model sees. It's the data that our model learns from. It's the data that our model is tested by, and it's even the data that our model sees in production that we may need to incorporate as well. And so for us to actually be able to create and produce models that reflect the changes in the real world, we need to figure out a way to manage these two life cycles. So even if we just bluntly applied testing and tried to incorporate these mechanisms together, there's a great paper called the ML Test Score paper that talks about how to incorporate these things. This is beginning to summarize what things are going to look like in the real world. So just as we tested for software bugs in our code, for instance, with unit tests and integration tests, we now have to also test for bugs in our data as well. And so that means that our machine learning systems, the testing and monitoring, should look similar to this. As before, with software development, all those considerations remain the same, except now we must place a lot more emphasis on the data test. And just as our code should be tested before it's ready to deploy, our data should also be tested to ensure that we have high quality data and that our model can learn from it effectively and that we can iterate to improve it. So how we manage the machine learning loop, how we actually complete the machine learning loop and do it well is to properly apply machine learning operations. And in a nutshell, machine learning operations is managing all the moving pieces of machine learning and operationalizing them. And so completing the machine learning loop actually means to correctly apply machine learning ops to your machine learning system. And so just as we use Git and GitOps to manage our code, we actually are going to need tooling to manage the data development process and the model training process, and even how we're pushing things to our production systems to monitor how these models are performing so that we can gain insights and continue the loop and continue to learn and improve. And so what we need is we need to record where things have been, what things have changed. We need to be able to test our code, our data, and our models so that we can ensure that we have reproducible experiments and deployments. And then we need to be able to monitor the performance and quality of our models and software. Now with code, we have tooling that's going to allow us to version things. But when we go to our data, how are we going to version our data sets? How are we going to iterate on them and then evaluate the effects and the effects of our changes on our models? And so, at least for myself, I realized this pretty early on when working with applied research teams. And we would, for instance, on speech recognition, again, we would build a model that performed amazingly well on our internal data sets. Some of you may be able to relate on this one. It would perform amazingly well on our internal data sets. But as soon as they reached the real world, we would get reports of poor quality. And so these issues could be due to artifacts in the audio. This could be due to accents that were present, or people cutting each other off in conversation, poor audio quality. There were many, many different things that could go wrong. And as soon as we saw these in production, this would cause us issues, and we'd have to start thinking through how we were going to solve this. And also, this would vary from institution to institution. So we knew we needed to iterate on our data, but we also knew that we would need to apply different data to different problems. So versioning and testing and automation and reproducibility, we were just wondering how we were going to manage all these moving pieces. And some of you may be in this situation today. We now want to turn our attention to a practical approach to machine learning ops, or practical approach to ML ops. And the reason we're talking about a practical approach and not saying, here's the solution, is because sadly, this isn't a solved problem yet. Today, we'll first start with where we are today to see why it's not a solved problem. So today we find ourselves in a situation where most companies using machine learning are really at the beginning of their ML ops journey. So they've seen what machine learning can do for their organization. So maybe they built a model, they put it into production, but as soon as they put it into production, they know they need to iterate. And now they're trying to think through and figure out how to streamline this process, how to remove some of the redundancies, and just get a better throughput for the organization or even just the model building process as a whole. And the problem there is that applying these machine learning ops principles is really hard. The decisions made around ML ops are typically much more complex and costly. So we've got to figure out how we balance everything. So for instance, in ML ops, your specific problem may have different data types, whether it's audio or video or images, text, whatever else. You may have scaling requirements, like how do we actually build a model that's going to scale up to whatever degree that is. And then there are different technical approaches, and these technical approaches change over time. And so this becomes an interesting question on how you balance everything and incorporate ML ops, because the decisions made around ML ops are more organizational and tooling, and retooling is a very expensive thing. So how do you balance everything? So this becomes even worse when we start thinking about security concerns or even data retention requirements and compliance. And then one step further, how we actually have various team members and team competition or compositions. So I know in some organizations, they may not have machine learning engineers, but may just have a collection of data scientists or different levels of technical ability. Maybe the data scientists are responsible for putting machine learning models into production. And so for machine learning to become pervasive, it really needs to become accessible. And the problem here is that smaller companies are not going to be able to build their own machine learning platforms and stacks. This is kind of where we are, I think, right now, is that we're in these early stages where we have many different tools, and a lot of them are considering ML ops and how we actually piece these things together so that we can enable continuous iteration on our machine learning models without having to reinvent the wheel every single time. And also they're building these tools and incorporating machine learning operations into these tools so that we can actually reach smaller companies where you don't have to have deep levels of expertise on every single thing to be able to leverage and get the benefits of machine learning at your organization. And one example of this is the AIInfrastructure Alliance. So the goal of this organization is actually to bring together different people and projects and even organizations to build out the future of machine learning. And they're trying to do this by establishing clean APIs and integrations and open standards to be able to even create stacks and solve the problems or set the interaction patterns to make sure that ML ops is consistent and AI infrastructure is consistent to solve many problems, because some companies may be much better in one area as another. So for instance, structured data should be and is handled very differently from unstructured data. And in order to build the best tooling that can handle these things, there isn't always a one size fits all for those types of things. So at PacketArm, we're trying to actually build the data foundation for machine learning. And what that means is that we're trying to build a platform that allows you to automate data pipelines while also versioning everything else in the process. So if we take a look at how PacketArm works, we do this by combining scalable data versioning systems. And so these are this is a Git-like versioning system. So we have data repositories and we're committing data to these data repositories so that we can track the history of how that data has evolved over time. And then we combine that with data-driven pipelines. And so these data pipelines are built on top of Kubernetes. They can connect to our data repositories, And the reason they're data-driven is that we can actually enable them to, every time that data changes, these pipelines run automatically. So this means that as changes are happening to our data, similar to a CI/CD system, all our data pipelines are running automatically. And so you can use these pipelines to retrain models. You can use them to automate testing for your data, or even like releasing versions of your data sets, et cetera, et cetera. And then the other benefit about these data pipelines is any of the artifacts that are produced. So for instance, a model or something else, those artifacts are also versioned. And so this means that at the end of the day, we can get a data lineage of everything that's happened. So any changes to our data, we can know exactly which pipelines are run, because this is running on top of Kubernetes. So there's a Docker image, and the exact version of our code is known whenever this pipeline is run. And we can say, we know that this change in our data set ended up producing this model, and we can go back and look at the deltas or the differences, similar to how we would in a Git type environment. But it doesn't just stop here. So PacketArm is a founding member of the AI Infrastructure Alliance, or AIA, the acronym's normally referred to. And we also know that there are some things that PacketArm should support rather than trying to do itself. So we have a pretty general architecture with data versioning and data pipelines, but there might be some things, there might be some specific ways that you want to train your model, or you want to monitor the training of your model that isn't exactly specifically what PacketArm does. And so this is why we're constantly working with AIA partners to figure out how and what we can do to best bring data versioning and scalable processing to these other tools and connect them with other tools, so that we can combine the benefits of our platform with other companies to create stacks that solve real world problems. And so here, this is actually one example of that. And so this is actually coming from the AI Infrastructure Alliance page, where we've looked at some of the work over there by Dan Jeffries, and others have done an incredible job at figuring out what are kind of the main components that need to exist in a machine learning stack. And this could be, and some of them are optional depending on what your task is. And but this is kind of an overview of all the different things that sort of need to be considered, or at least thought through on whether or not you actually need these for your application. So we can see that in this scenario, we've talked with a few of the partners inside the AI Infrastructure Alliance to see where we overlap, where we maybe complement or even fill a void in the stack compared to some of the others there. So we can see in this picture where the divisions of labor exist and how tools complement each other. So for instance, we might want to use Seldom for our deployment engine, because they have all kinds of interesting things around detecting model drift and other things like that. But all the while, maybe they need some type of versioning and storage, and even just automation of the pipelines that are actually deploying these things to production. So we've done a coupling there where we can work together to help build a stack that's going to allow people to complete the machine learning loop without having to figure out all of the problems or have one solution that's trying to serve multiple end goals. And so this is still in the early days, and it's also a relatively optimistic view of the world and how we work together. But we know that if we truly want machine learning to be a completed process, if we want to be as efficient with creating machine learning models and having machine learning be a part of everything that we do, then we're going to need to have a stack like this. We're going to need some type of infrastructure that's going to allow us to iterate quickly and to be able to be approachable and address the masses that are interested in working with machine learning. And so we're still in the early days of these types of stacks, but there's some really great progress being made. So as we're coming to the end of our talk, I just wanted to do a quick summary and conclusion. We started off with talking about that improving anything in the real world, but improving anything, it's going to require some iteration. And then we talked about how machine learning actually has two life cycles. We have a code life cycle and a data life cycle. And that to be able to do machine learning well, we need to be able to iterate on these two life cycles reliably and even handle the interactions between the two. The title of the talk, Completing the Machine Learning Loop, really means that we want to support the iteration for both of these, but we want that to be supported in a graceful and reliable and resilient way. And so what we did is the way we approached that is we tried to learn from DevOps. We tried to look at how DevOps has improved the software development industry and how it's improved the reliability of releases by applying testing and continuously releasing. And then finally, we applied this to machine learning. We wanted to think about how we applied this to our tooling and our processes from an abstract standpoint. And then finally, we took a look at PacketArm and then some of the others in the AI Infrastructure Alliance to find out how these things could work together and how we're already seeing some of them working together in order to build what we're calling the canonical stack, a term coined by Dan Jeffries, the canonical stack for machine learning, so that we can have a reliable way or something to iterate on to continue to complete the machine learning loop, to bring machine learning to the forefront and expand its use across the world. So with that, I think we're going to stop there and maybe move into some Q&A, but make sure you check out PacketArm, check out PacketArm Hub, which is our hosted version of that, where you don't have to know Kubernetes. The AI Infrastructure Alliance, I think there's about 60 different companies or organizations that are in that now. And if you have any questions about this, definitely feel free to reach out on Twitter or contact us to learn more. So thanks so much.